So, welcome all of you. In the last class, we started discussing about carbon 13 NMR, which is another very important exotic nuclei, very friendly nuclei because spin half, but of course, it has less abundance, only 1% of the 2 isotopomers of carbon. Carbon 12 is major isotopomer with 99% abundance. Carbon 13 is spin half, that is NMR active, carbon 12 is NMR inactive, and this is present only in 1%. And also as a gamma is 4 times less than that of the proton, it is very less sensitive. That is what I said. And also I said, if there are n chemically inequivalent carbons present in the molecule, usually all the carbon 13 spectra are recorded with broadband proton decoupling. That means we decouple all the protons present, all the protons coupled to carbon. Overall simultaneously all the carbons coupled to all the protons are broken. As a consequence, you are going to get a single peak for each chemically inequivalent carbon. That is why carbon 13 spectrum is fairly simple to interpret. But I said if there is abundance is only 1%, probability of seeing carbon in carbon 13 state is only 1% when there is single carbon. What happens when there are 2 carbons? I said probability is 1 in 10,000, 0.000121 I so told you. What happens if there are n number of carbons? I took the example of 3 and then 6. If there are 6 carbon present, I said the probability of seeing all the carbons in the carbon 13 state is 1 in a quadrillion, 1 in 10 to the power of 12. Huge, very if you have very small abundance of such molecules, practically it is impossible to get the spectrum from such molecules. But in reality, even for a big molecule with large number of carbons, we do get the spectrum. Then the question is, how do we get such spectra? For this I also explained to you, taking an example of ethanol, when there are 2 carbons present, each carbon can be individually present in carbon 13 or both carbon 13 and both carbon 12. That is what I explained. And both present carbon 12 is NMR inactive, does not give signal. Both carbon 13 present is very difficult to see, probability is very low. And only carbon there are 2 isotopomers, CH3 with carbon 13 per state, CH2 in carbon 13 state will give rise to NMR spectrum. And there is a 1 bond coupling. I explained to you when there are different carbons attached to different number of protons. Carbon attached to CH3 group, for example, 3 protons gives a quartet, CH2 carbon gives a triplet, CH carbon is a doublet, and quaternary carbon does not give any, it gives only a singlet, no coupling. That is what I said. And then extending that logic, if I go to ethanol spectrum, CH3 will be a quartet and CH2 will be a triplet. But there is also long range coupling. CH3 carbon can couple to protons of CH2. CH2 carbon can couple to protons of CH3, in which case spectrum gets complicated. One it is going to become a quartet of triplet, other is going to be triplet of quartets. That is a real spectrum, fully coupled carbon proton spectrum. But I said we are going to do the decoupling. When you do all the proton carbon decouple remove, you will get one single peak for each of them. But I also said if you look at the proton coupling, protons are passive spin and they are not getting reflected in the carbon 13 spectrum. This is what we understood. So with this now we will go further, and I told you for a molecule containing n chemically inequivalent protons, the proton spectrum is from a single molecule. Whereas the carbon 13 spectrum, if in a given molecule, if there are n chemically inequivalent carbons, there will be n different isotopomers, in which each isotopomer has carbon in carbon 13 states in different carbons. In one molecule, one isotopomer, one carbon is carbon 13, another isotopomer, different carbon will be in different carbon 13 state. Like that, you have n different isotopomers, each having carbon in carbon 13 state. So the real carbon 13 spectrum is not from a single molecule. It is superposition of the spectrum of all the different isotopomers. That is what we saw for ethyl alcohol. That is what I said in this case. So now we are going further. We can see diethyl phthalate, a simple molecule. This molecule spectrum is chosen because it is very simple. We have CH3, CH2 here. See, look at it, CH3, this CH3 here. It is a quadrat. As I told you, 3 protons coupled to carbon will make this carbon a quadrat. But these remote protons also coupled to this long range and makes this, it is going to be triplet of quadrats. Similarly, CH2 is going to be CH2 is a triplet because of 2 protons coupled to carbon, and then long range coupling make each of them as each line of the triplet as a quadrat. It is going to be triplet of quadrats. And we also have 3 different protons. There is a symmetry along this axis for this molecule. There is a quaternary carbon, and these 2 protons are single proton attached CH carbons. So, as a consequence they are doublets, but of course they can have a long range couplings. So, this is a very simple spectrum of this molecule. I just wanted to show you, if you look at the carbon 2 here or carbon 3 here, for example this is a carbon 3. It has a 1 bond coupling with carbon proton and there is a long range coupling with different protons. This carbon can have a coupling with this proton. So, that is what we are going to see. It is a complexity will be there. Similarly, if you come to carbon 2 has a long range coupling with 1 bond carbon direct 1 bond proton carbon coupling. At the same time, it has a long range coupling with protons attached to carbon 3. So, it is going to be complex like this. So, that is how you can interpret, and then since it is going to be a decoupled spectrum, this much of complexity won't be there. You simply look for each peak and 1 peak for 1 carbon. So, that is why I said broadband decoupling is an important thing which we do in carbon 13 NMR. Before going to that broadband decoupling, I want to give you the strength of couplings, because that is important. The broadband decoupling requires irradiation with a radio frequency with another radio frequency at the proton frequency, and the strength of this radiation should be larger than the coupling strengths. Then only you can break the coupling. Okay. So, for that we should know the strength of J coupling. 1 bond J coupling normally is of the order of 150 hertz. It can go to 200 or 250 hertz. It is not a dogma. In some molecule you can go up to 200. In some molecule we have seen up to 250 also. Similarly, if you consider the molecule of this with 2 bonds, with 2 bond carbon proton coupling, it can vary to 2 to 10 hertz. And 3 bond, it can be 2 to 10 hertz again. And it can so happen sometimes 3 bond couplings is more than 2 bond coupling. That is also possible. Varieties things can happen. This is just an idea, so that we should know how much RF power we have to apply to break the coupling between carbon and proton. And what are the J values for different type of molecules? If you take benzene group, 1 bond CH coupling is 127 hertz. For a 5 member ring 131, 4 member ring CH coupling here is 136, 3 member 161. See this one with 3 member with O attached 175. You see, as the size of the ring keeps coming down, the coupling strength keeps on increasing. These are typical 1 bond carbon proton couplings in different molecules. And in a linear molecule, chain molecule like aliphatic group present, this 1 bond coupling carbon proton and 1 bond carbon proton to this one for CH3 group, CH2 group is of the order of 125. For in a group molecule like the CH3OH is 142. If you have a group molecule like this, 1 bond coupling between carbon proton is 155. Wherever I have highlighted, it is that carbon coupled to its attached proton. For example, in this molecule, this CH2 coupling is 160 to 170 hertz. Come to this phenyl carbons. See, this is a strange example. In the phenyl group, the carbon attached and there is another triple bond CH. The coupling can be 250 hertz, quite large. Take for example CHCl3, coupling is close to 210 hertz. So, this is how we know the values of different carbons, strength of the couplings of different carbons with 1 bond coupling to its directly attached proton. So, a real complex spectrum we will see. Look at the spectrum. It is a very, very complex spectrum of a cholesterol. How many carbons present in that? You can count yourself 1, 2, 3, 4, 5, so many carbons are present. Now we know how you got the spectrum. I already explained to you. This is superposition of spectra from several isotopomers. Each time 1 carbon is in carbon 13 state. That is the spectrum we got. So complex with all proton couplings, you see. You can easily identify here the patterns. For example, here is a quadrat. For example, this is a doublet like this. How do you simplify this analysis? There are so many multiplicities present here, they are overlapped. How do you identify triplet, quartet, etc. multiplicity? What we do is, we simply do the decoupling. When we do the decoupling, this complexity of the spectrum gets enormously simplified. Now the question is, what is decoupling? I vaguely discussed this thing earlier, and I just wanted to tell you this has been discussed extensively in one of the previous courses. Just for idea, the broadband decoupling of carbon 13, how it is done is, you see, we are going to apply a radio frequency pulse on carbon, start collecting the signal, and then we are going to apply another RF pulse at the proton channel, at the proton frequency. This is called a broadband with a continuous wave decoupling. Continuously we keep on applying RF pulse with a high power. Power is such that it should be larger than, at least 2 times larger than the carbon proton coupling. In which case, what is going to happen is, you will break the coupling between carbon and proton. See what happened? In reality, this is diagrammatically like this. At the proton frequency, you keep on applying RF to saturate proton. What do you mean by saturation? We already discussed in the very first or second class. Saturation means where the population between two energy states are equal, or in such that you keep on when applying RF power in such a way, the spins in the lower energy state goes to higher energy state, and spins in the higher energy state will come to lower energy state, and this rapidly happens when you continuously pump the RF power. Then what will happen? This carbon will not see this proton in alpha state or beta state, neither of the states, because there is a rapid transition going on between two states. It will see, or in other words, it is saturated, it will not see any population at all in either alpha state or beta state. Then it will see the average, neither alpha nor beta is somewhere here, in which it appears as if it is not coupled at all. You have broken the coupling. This is what is called decoupling, and we are going to collect the signal while applying the RF pulse continuously. You collect the signal on carbon 13. This is what we do. So that means when you are applying the another RF power at the proton channel and you collect the signal, you will break the coupling between all protons coupled to all the carbons. So irradiation, this is what I said, causes proton to get saturated, and the spins undergo rapid transition among all the possible spin states. The carbon nucleus senses only the average spin state, not either alpha state or beta state. There are n number of distinct spin states, it does not see all of them, it will see only the average. So in effect, all the spin interaction between carbon and proton are averaged to 0. This is because of rapid transition of spins among the spin states. This is what is called broadband decoupling. Broadband because broad range of frequencies of all carbon to all frequencies will be broken. This is called broadband decoupling. Now the question, as I already told you, how much of the RF decoupling power you have to apply? It should be at least twice larger than the largest CH coupling. The CH coupling in the molecule is, let us say, 250 hertz. At least the RF power should be larger than double of that, about 500 hertz, just to be sure. Even more than one CH is enough, but to make sure that there are no other effects, we have to make it double of that, so that slightly larger, and in such a case all the carbons coupled to all protons are removed. And where do you put this RF? Where do you send the second RF to saturate protons? At the center of the proton spectrum. Remember, carbon is coupled to proton. We have a proton spectrum. Go to the proton spectrum here, go to the center of this proton spectrum. At that place you apply the RF power. When you apply the second RF, decoupling RF, then this thing happens. So this offset, decoupler offset has to be set to the center of the proton spectrum, and its power should be at least twice larger than the CH coupling. And the broadband spectrum, as I told you, gives us a single and a distinct peak for each chemically inequivalent carbon. Very simple. Okay. Now take the example of this molecule. How simplified, how the coupled and decoupled spectrum appears. This is a molecule, some phenol, recorded at 75 megahertz. So proton frequency is 300. This is the spectrum without any decoupling. We have CH3 group, CH2 group, and phenyl group. CH3, as I told you, when it is coupled, it will be a quartet. 3 protons are coupled to this carbon. CH2, both these protons are coupled to this carbon, a triplet. And each of the CHs, there is symmetry here, and they are equivalent. 3 and this thing and this are equivalent. So there are only 3 chemically inequivalent carbons. Each of them is a doublet, because it is attached to single proton. Very nice. At the same time, there is also a carbon, ipso carbon, which is not attached to any proton. That is called a quaternary carbon. Now, this is the total spectrum. Here it is easy, simple molecule. I can interpret. What happens in a big molecule is difficult. So, to understand decoupling, we do the decoupling, proton decoupling for this carbon 13 spectrum. Now, what happens you see? This quartet coupling disappears and all the peaks merges into a single peak. So, you will get a single peak at the center of this multiplicity that correspond to chemical sheet of carbon CH3. Similarly, this triplet, all the lines will collapse and appear at the center of this. That is the chemical sheet of carbon CH2. Similarly, chemical sheet of the different carbons here, and this is a quaternary carbon. And so, you see there are 6 carbons here in this molecule, there are 6 peaks. That is the difference between coupled and decoupled spectrum. You can, if you want to go further here, you can see the changes what we see here. More important thing I showed you in the cholesterol molecule. This is where you see. This was the quartet, this is coupled and this is Broadband decoupled. Look at this is a quartet. This is okay doublet. I can understand this also doublet. What do you get out of this? It is a clumsy thing, you do not know, but there are so many carbons present here. So, what we do is we do the Broadband decoupling and then we identify the number of carbons present in that very easily here, which is not possible from this. Okay. This is the carbon 13 Broadband decoupling we do. But then just to give you an idea, how do we do the Broadband decoupling? I already told you. We apply the RF power at the proton frequency and saturate the protons while detecting the carbon. That is decoupling, a hand waving argument. This Broadband decoupling can be done in different ways. What are those different ways? First of all, I can acquire the carbon 13 spectrum with different ways. Before going further, here I want to tell you one thing. I am using the word term called NOE, meaning nuclear overhauser effect. I have not discussed this, that is to be extensively discussed. After this carbon 13, maybe after heteronuclear, I will introduce NOE. And also I am going to introduce one called depth, polarization transfer is needed. That also I have not explained, but that is used in this class in understanding carbon 13 NMR. Both polarization transfer and NOE will be discussed subsequently in the remaining classes. But please remember, NOE is an enhancement of the signal because of decoupling of one. Then what will happen? The neighboring carbon or neighboring proton will have a enhanced signal intensity. This is because of overhauser effect. This is called nuclear overhauser effect. I will discuss this later. So, now I can have a coupled spectrum with NOE, meaning I am going to apply a radio frequency pulse and collect the signal on carbon 13. X is carbon 13 for me. But what I am doing? Remember, on the proton channel, but there are different channels. On the proton channel, till we acquire signal, before this, we are applying decoupling power. And then I am collecting the signal. Here, RF power is not applied. That means here I am not decoupling. I am going to get a coupling here. But why did I apply decoupling power before? That is a phenomenon. When I do this, applying decoupling power, prior to that, we get enhancement of the signal intensity due to overhauser effect. This is an experiment. If you do, you will get a coupled spectrum, but with enhanced intensity. This is called coupled spectrum with NOE. On the other hand, I can do one more thing. I can start acquiring the signal and don't do NOE at all. This is a spectrum where, because I am applying decoupling power while acquiring the signal, I am breaking the coupling between carbon and protons, but I am not doing NOE. There is no NOE here. This is what is called inverse gated decoupled experiment. This is called inverse gated decoupling experiment, where I am decoupling the carbon with protons, but no NOE. There is no enhancement in the signal intensity. This is an experiment, but NOE develops and affects the longitudinal magnetization. So, as a consequence you do not get the thing. So, since the accusation is already present here, there won't be build up of the signal. That is why this is called inverse gated, no NOE, and we are going to decouple. I can think of other situation. I can apply continuous RF power, maybe of different strength. This is different strength, this is different strength. Can use similar strength, no problem. This is called high power decoupling. I have a NOE, at the same time I am also doing decoupling. This is an experiment. The decoupler is on continuously throughout the experiment. Even before applying the pulse, after applying pulse, while collecting the data, continuously RF power is on at the proton channel, at the proton frequency. This is an experiment called high power decoupling. Here both decoupling is going on and NOE is going on. Simultaneously both are going on. Then what you are going to get here? You are going to get a decoupled spectrum, completely removed carbon proton coupling, plus signal intensity will be enhanced because of NOE. This is a decoupled spectrum with NOE. Okay. And this is the routine carbon 13 NMR all of you will be doing. Remember, this is the when you record a carbon 13 NMR spectrum, this is what you are doing. Without your knowledge, the operator will be recording this spectra for you. And look at the example, how do we compare this thing? This is a carbon 13 NMR spectrum of this molecule. Very complex. It is a coupled. Coupled means each of this carbon has multiplicity pattern because of coupled protons, quadrate, doublet, all those things, triplet, etc. all are overlapped here. You see, look at the spectrum, it is very clumsy, lot of noise is there, very noisy here. On the other hand, we do this gated decoupling. What is gated decoupling? Inverse decoupling, I told you. We are applying, we are doing the coupling, at the same time we are doing NOE before applying RF pulse. That is called inverse gated decoupling. When you do that, you see still you get a coupled spectrum. Okay. But at the same time you will see this is still a triplet. You see here this is still a triplet. We are not decoupling, we are it is coupled, but NOE is there. Because of NOE you can see the intensity here, enormous rise in the intensity here. Look at the signal here, look at the signal here. We still got the coupled spectrum, but with the enhanced intensity, this is a gated decoupled spectrum. Coupling with NOE is there. Coupled spectrum plus NOE. Same thing you can do in a different way. You can do decoupling with NOE. You see, look at this one now. Completely all the proton carbon couplings are broken. You get an enhanced intensity. Look at the signal intensity here. Look at the signal intensities here. Signal to noise ratio is very poor here. Look at this one, huge signal and very little noise here. This is a real CW spectrum with decoupling, and of course there is NOE there. Okay. And this is with inverse gated decoupling for the another molecule, just to compare no NOE and this is a decoupled with NOE. Where you see the effect? You see the effect here. Look at this peak. Look at this peak. Look at this peak. Enormous gain in the intensity. This is all because look at this ratio here. This is because of NOE. So this is the way how we can enhance the signal intensity of the carbon by doing decoupling with NOE. And this comparison will tell you this is a spectrum without any decoupling. Can you see this one? So signal to noise is so poor, peak signals are very weak intensity. No decoupling because there is a lot of multiplicity, each peak split into multiplicity, doublet, triplet, quartet like that. As a consequence, signal to noise ratio is very poor. This one gated decoupling, that is coupled spectrum with NOE, same thing with signal intensity more. See the comparison, already you have got better signal to noise ratio. Go further, this is a inverse gated decoupling, decoupling without NOE. I am decoupling here but no NOE, and the last experiment decoupling with NOE. Fantastic, there are 4 possibilities: no decoupling, coupled with NOE, decoupling with NOE, and decoupling without NOE, and decoupling with NOE. And decoupling with NOE is the real spectrum. Compare this and this, all multiplicities are broken here, and we are going to get a singlet for each carbon. Plus look at the enhancement in the intensity, huge intensity is there. So, this is what is important. Signal intensity goes up because of NOE in a record spectrum of carbon with decoupling with NOE. What you have to do for that? You have to put the decoupler power on throughout before acquiring the signal, before you apply the pulse, while after applying the pulse, even while acquiring the signal, continuously decoupler power is on, in which case you are going to get this one. And this is a simple comparison for a sucrose molecule. 4 beautiful spectra here. See, this is a spectrum, no decoupling, no NOE, inverse gated decoupled, no NOE. This is gated decoupled NOE, this is broadband decoupled NOE. Look at here to here, what a gain in the intensity you are going to get. And this is the experiment all of you would be doing every day. Okay? This is what I wanted to tell you about decoupling. I hope you got the feeling about decoupling. Okay, we have got individual peaks for different carbons. But how intensities are same? Here look at this example. You go here, somewhere here, this also okay, this is not bad. Here, for example, if you look at this one, you will see that different carbons have different intensities. What did I say? Each peak corresponds to one carbon because it is decoupled. That is what a carbon 13 is recorded. If that is the situation, when each carbon corresponds to each peak corresponds to one individual carbon, why there should be difference in the intensity? Or carbon should be of identical intensity, right? There should not be any change in the intensity. But actually, in reality, the intensity of the carbon 13 spectrum all are not of same intensity. They are different. Why? It is because of symmetry and relaxation. Different carbons have different relaxation times. At the same time, molecular symmetry also ensures that some carbons have double the intensity or some have less intensity. This so intensity of the carbon 13 peaks depends upon symmetry of the molecule and how individual carbons are relaxing. Okay? Look at this molecule. It is a simple molecule. So, we have a symmetry along this axis. 3 molecules are there. Okay? We can, I am putting this into this format. Now, there are symmetry if you consider how many chemically inequivalent carbons are there. You put this one carbon, these 2 are equivalent, these 2 are equivalent, these 2 are equivalent and these 2 are equivalent. So, how many carbons you get? 4 different carbons and each of them double intensity. So, but they overlap, you get 4 peaks. That gives 4 peaks. And what about this one? There is a perfect symmetry along this axis and along this axis. Now, all the CH3 carbons are equivalent and both these carbons are equivalent. So, how many peaks you get? 2 peaks. But what is the intensity? This is 1:2 intensity. These 2 overlap and give 1 peak. These 4 will overlap and 1 peak. The intensity ratio is 1:2 or 2:4. Okay, there are 2 peaks. Look at predict the number of carbons seen in these molecules. How many carbon peaks we expect in this molecule? If I ask you the question, draw the symmetry axis here. How many different chemically inequivalent carbons are there? 4, because this and this are same, this and this are same, this carbon are different. You get 4 peaks. What about this one? There is a symmetry axis here. This carbon is same, this and this are same, this and this are same, this and this are different. So, how many carbons you get? 1, 2, 3, 4, 5, 6. See, 5 carbons are there. What about this one? There are 6 carbons. All are chemically inequivalent. 1, 2, 3, 4, 5, 6 carbons. So, similarly this one, this molecule has 5 carbons. So, this is how it goes, and you can even predict the reaction product just by looking at the carbon 13 spectrum. Take for example a molecule like this. Somebody was doing a chemistry reaction of this molecule with KOH and he was confused whether you get this peak or this peak. I mean this molecule or this molecule. How do you know which is the molecule? You have the reaction and this is the product. Which is the product? Simply what you do is take a carbon 13 spectrum of this molecule. If this is your product, for example this one, how many peaks you expect? if this is the product, you get 7 lines. All carbons are inequivalent. See, there is the double bond here, there is no double bond. These 1, 2, 3, 4, 5, 6 all are different, and this one 7 carbon. Whereas here there is a perfect symmetry axis. So this is same, this, then this. There are 5 carbons. So what you do is, when you do this reaction, take the product, take the carbon 13 NMR spectrum, and if you get 7 lines, then this is the product. If you get 5 lines, this is the product. You do not have to even worry about interpretation. Just count the number of lines, then you know what is the product of this reaction. So you can predict the reaction based on the symmetry of the, it's based on the number of peaks you get, which depends upon the symmetry of the molecule. So that is what I was telling you, the number of peaks that you are going to get in the carbon 13 and its intensity depends upon relaxation and the symmetry of the molecule. How do you know it depends upon relaxation? This is an example now. Look at this molecule which we already analyzed. This is a spectrum taken in a conventional way, where signal keeps on acquiring. We acquire signal one after the other several number of times to enhance the signal intensity. But the relaxation delay is kept smaller than T1, smaller than longest T1, whatever the carbon which has longest T1. For example, the T1 of the carbon is 5 seconds. You set the relaxation delay between the time delay you give between the pulses, different pulses to acquire the signal. You keep it less than that, maybe 2 seconds or 3 seconds, acquire the signal, and this is what you are going to get. See, for example, this carbon intensity, this carbon, they are not of equal intensity, but they are individual carbons. Why we are not getting individual carbon? See, when there is a overlap, I understand. When there is no overlap, why we are not getting individual intensity, equal intensity? So then that is a problem. So that is one aspect. It is a possibility because we are given relaxation delay less than that. On the other hand, we can do inverse gated decoupling with same to enhance the signal intensity. Identical experiment with the inverse gated decoupling, that means there is NOE. But still the relaxation delay is less than T1. But that has not helped you. That has not made all the peaks are equal. Equal intensity of all the peaks are still not equal. That is a problem. So on the other hand, do the last experiment. Relaxation, I mean they say inverse gated decoupling you can do with NOE. Give the delay larger than T1, not just larger, it should be 5 times T1, 5 times the longest T1 of the longest carbon which has the longest T1 you have to consider. Give that much delay. You understand? For example, different carbons have different relaxation time. One may have 1 second, 2 second, 3 second, 4 second. I have not discussed relaxation in this course, but I have discussed previously. But when there is an opportunity comes, I will talk about relaxations soon, maybe after a couple of classes. But different carbon may have a different relaxation time. Consider the carbon which has the longest relaxation. Give 5 times that and record the spectrum with the same NOE. Look at it, what is happening. All the carbons are of equal intensity. And this is the beauty. So what is important is the relaxation also matters and the symmetry also matters. Example of the symmetry and the relaxation both defined in the non-protonated carbons here. You see, ipso carbons is paracarbon, no, only this ipso carbon. These are all protonated. They have different intensity. Ipso carbon not attached to carbon, not attached to proton. This carbon has a very weak intensity because such carbons relaxes very, very slowly. This is okay, intensity ratio 1:2 is understandable, whereas this one is not understandable. That is because non-protonated carbons always relax slowly. So this is how we can get the understand about the peak intensity depends upon the symmetry and the relaxation of the molecules. So what I am going to do is, we will understand more about the interpretation of the carbon 13 spectra and little bit more details in the next class. Right now in this class what I discussed about is varieties of decoupling techniques available in carbon 13 which enhance the signal intensity. Finally, what you are going to do is a broadband decoupled with NOE, that is the CW decoupling. Continuously you apply RF power both before applying the RF pulse and after applying the pulse while collecting the signal. And the decoupling power should be applied at the center of the proton frequency. When you do that, you get a spectrum fully decoupled and the intensities differ because of the symmetry of the molecule, depends on the relaxation time of different carbons. Do an experiment with gated decoupling or CW decoupling, whatever it is, with a relaxation time delay given 5 times the longest T1 of a given carbon in a molecule, then you get all peaks are of equal intensity. Usually quaternated carbons which are non-protonated have less intensity. So, intensity depends upon the symmetry of the molecule and intensity depends upon the relaxation time of the molecule. So, this is what we generally discussed about it, and I also discussed what is the decoupling, how much, what do you mean by decoupling, how much power you require for decoupling, broadband decoupling of entire carbon, all carbons with all protons. So, with this idea we will stop here, we will come back and continue with the next class where we discuss much more about carbon 13 NMR. Thank you very much.